Have you ever really stopped to wonder what's going on inside the mind of an AI? I'm not talking about the massive neural networks we hear about all the time, but the real, fundamental, logical bones of how a machine is taught to think, to strategize, and to solve problems. Well, today, that's exactly what we're going to do. We're exploring the very building blocks of machine reasoning.
It really all comes down to this one big question, right? And of course, there's no single answer. So instead, we're going to take a tour of three totally distinct ways AI is built to tackle problems. First, as a competitive player in a game, then as a meticulous puzzle solver, and finally, as a logical detective trying to make sense of an uncertain world.
All right, first up, let's talk about the strategic competitor. This is the kind of AI you'd picture sitting across a chessboard from a grandmaster. It's designed specifically for what we call adversarial situations, zero-sum games, where if one side wins, the other has to lose. Its entire purpose, its whole reason for being, is to outthink and outmaneuver its opponent.
And to do that, it uses this incredible technique called adversarial search. See, the AI doesn't just plan its next move. It explores this massive, branching tree of possible futures. It simulates its own move, then it simulates its opponent's best possible response, then its own best countermove to that, and on and on and on, peering deep into all the potential ways the game could play out.
Now, at the very heart of this is something called the minimax algorithm, and it is such a beautifully simple yet powerful idea. The AI sees itself as the max player, always trying to get the highest possible score. But, and this is key, it assumes its opponent is the min player, who will play perfectly to force the lowest possible score for the AI. It's kind of like this dance of pure logic and a healthy dose of paranoia.
So this slide right here shows exactly how that decision gets made. The AI looks all the way down at the final outcomes at the bottom of the tree, the wins and losses. From there, it works its way back up, and at each step, it assumes the opponent will pick the move that's worst for the AI. This whole process, called backing up the values, lets the AI at the very top of the tree choose the one single best move that guarantees the best possible outcome, even in the worst-case scenario.
Okay, so minimax sounds brilliant, right? But it has this one huge show-stopping flaw. For it to work perfectly, it has to generate the entire game tree all the way to every possible checkmate or draw. And for any game more complex than tic-tac-toe, that is just computationally impossible.
Just to give you a sense of scale, let's talk about chess. The average number of possible moves from any position, we call that the branching factor, is about 35. And an average game lasts about 100 moves. So the number of possible game states is 35 to the power of 100. I mean, that number is so unbelievably vast, it makes the number of atoms in the entire known universe look tiny. Brute force is, well, it's just not an option.
So, if the AI can't just outmuscle the problem, it has to outthink it. It's clear it can't explore every single branch of that enormous tree. But what if? What if it could figure out which branches were dead ends without even having to explore them?
And this is where the magic of alpha-beta pruning comes in. It's an optimization that is, frankly, genius. It allows the AI to literally prune, or just cut off, huge sections of the game tree that it knows, with absolute logical certainty, cannot possibly contain the best move. It's like having a logical shortcut through a maze.
And this slide right here shows you how it works. Once the AI finds a path that guarantees it a certain score, let's say a score of 3, it uses that as a benchmark. Now, as it explores other branches, if it stumbles into a situation where the opponent can force an outcome that's worse than 3, the AI can just immediately stop. It completely ignores that entire section of the game. Why? Because it's already found a better option, so there's absolutely no reason to waste time on a path it knows is inferior.
Okay, let's shift gears now. What if, instead of an opponent, the AI's challenge is just a really complex puzzle with a whole bunch of strict rules? Well, this brings us to our second AI mind, the clever puzzle solver.
The framework for this kind of thinking is called a constraint satisfaction problem, or a CSP, and it's actually a very neat structured way of defining a problem. You basically have three things. You have variables, the things you need to find a value for. You have domains, the list of all possible values for each variable. And finally, you have constraints, the set of rules that your final answer absolutely has to follow.
A classic example of this is map coloring. So here, the variables are the different regions of Australia. The domain for each of those variables is just the set of colors we have, let's say red, green, and blue. And the big, crucial constraint is that no two regions that touch each other can have the same color.
So how does an AI even begin to tackle this? Well, it doesn't really see a map of Australia. It converts the problem into a more abstract thing called a constraint graph, just like this one. Each region becomes a node or a dot, and a line or an edge connects any two nodes that are next to each other on the map. That edge basically just represents the constraint. These two nodes cannot be the same color. Now the problem is just a matter of assigning values to the nodes in a way that satisfies all those rules.
And this CSP framework is incredibly versatile. It can also be used to solve things like cryptarithmetic puzzles. You've probably seen this famous one. The variables are the letters, S, E, N, D, and so on. The domain for each letter is the set of digits, 0 through 9. And the constraints are that the math has to work out correctly, and, just as important, each letter has to stand for a unique digit.
So we've seen an AI that plays to win, and we've seen an AI that solves puzzles. Now, let's meet our third mind, the logical agent. This AI is like a detective. It gets dropped into an unknown, potentially dangerous place, and it's forced to use pure deductive reasoning to survive and, hopefully, achieve its goal.
And its training ground is the infamous Wumpus world. It's basically a grid-based cave system. Our little agent's mission is simple. Find the pile of gold and get back to the entrance. Easy, right? Well, the cave is also filled with dangers. There are bottomless pits and a terrifying monster called the Wumpus.
So here's the crucial part. The agent can't actually see these dangers directly. It has to rely on its percepts, its senses. In any square that's right next to a pit, it feels a breeze. In any square next to the Wumpus, it smells a horrible stench. These are the only clues it gets to try and piece together a mental map of the world and figure out which squares are safe to enter.
To make all of these deductions, the agent builds what's called a knowledge base. You can think of it as a collection of facts that it knows for sure are true. And then it uses two really powerful reasoning strategies to expand that knowledge: forward chaining and backward chaining.
Let's break these down real quick. Forward chaining is data-driven. It starts with the facts. The agent is in a square, it perceives a breeze, it adds that fact to its knowledge base, and then it asks, okay, given this new fact and all the rules I already know, what new things can I logically conclude? Backward chaining is the total opposite. It's goal-driven. It starts with a question, a hypothesis, like, is the square at 2-1 safe? And then it works backward, trying to find a chain of existing facts and rules that can prove that its goal is true. And this visual shows the difference perfectly. Forward reasoning is like this explosion of possibilities based on what you know. You start with your facts, and you just see where they lead you. Backward reasoning, on the other hand, is way more focused. You have a very specific thing you want to test, and you search for a specific path of logic to support it. Really, one is about exploration, the other is all about confirmation. So, there we have it. We've toured three very different approaches to making a machine think. We had a game player, a puzzle solver, and a logical detective. And even though they seem totally distinct, they are all built on the exact same foundation: formal logic. So, to recap, we've met these three fundamental minds of AI: the strategic competitor, the clever puzzle solver, and the logical detective. And these aren't just some historical footnotes, you know. They are the rule-based systems that still form the absolute bedrock of complex decision-making in AI today. They represent the classical, explicit way of programming intelligence. And that brings up a really fascinating final thought. We've seen just how powerful these logical building blocks are: the formal rules of reasoning, of strategy, and of deduction. So what happens when you give these tools for perfect, tireless logic to a machine that can also learn and adapt at a scale that we can barely even comprehend? That, right there, is when the future of reasoning really begins.